And today we have quite an interesting agenda of presentations that we want to share with you of work developed during the project. We will start with a brief introduction, which is what I'm doing right now. By the way, my name is Lucia Barbu. I'm a researcher at the International Center for Numerical Methods in Engineering, FIMLE. I'm an assistant professor here, and also I'm an assistant professor at the Polytechnic University of Catalonia. But today I'm speaking as the coordinator of the Fatigue4Light project. Now, we have several presentations. I will begin our webinar by giving you a general overview of the work plan we followed in the project and some interesting results, although very brief, of course. And after that, we will focus on the numerical methodology we have developed during the Fatigue4Light project to address fatigue simulation. And specifically, we will have a presentation titled Numerical Analysis of Steel Multimaterial Analysis from a monotonic and cyclic perspective, which will be given by Sergio Jimenez, my colleague here at FIMLE, also an associate lecturer at the Polytechnic University of Catalonia, and also a coordinator of the Fatigue4Light project. After that, we will speak about advanced high-strength steel lower control arc, the innovation we brought on this specific component during the project, and the presentation will be given by Michele Tedesco, which is the global responsible for metals and anti-corrosion at Stellantis at CRF. We will continue with the presentation centered on hybrid manufacturing and structural testing of a 3D-shaped fiber metal laminate, given by Matthias Merkvik, which is a senior scientist, who is a senior scientist at RISE, also partner in the Fatigue4Light consortium. And we will close with numerical simulation of the Fatigue4Light demonstrators. Again, an overview given by Sergio Jimenez, by my colleague from FIMLE. Now, during the presentations, if you have any questions, please write them in the chat, okay? So you can ask, write them in the chat. And at the end of these presentations, at about 11:20, we will have a question and answer session where we will address all the questions that you've sent, or if not, I can propose some additional questions. And it's generally, I would say, an open space for debate and discussion. So if you have any comment that you want to make, any discussion, any point that you want to put on the table, this is the moment to do so. We expect to close the webinar at about 11:40. Okay, so I believe nothing else from my side. We will get to the questions and answers when the moment comes. Let me go and start with the presentation on the general overview of the Fatigue4Light project. Okay, and I think we are, well, almost on time. Now, about the Fatigue4Light project, and I hope all of the people that have joined this webinar and have taken the time to be here with us today have curiosity about our project. The official title is Fatigue Modeling and Fast Testing Methodologies to Optimize Part Design and to Boost Lightweight Material Deployment in Chassis Parts. So definitely our project, let's say, I would say keyword is fatigue, okay? It's focused on fatigue, and specifically applied to chassis components, with an overview of finding what are the most appropriate new materials that can be deployed on chassis components to save weight, but also to make sure that we keep this optimal fatigue performance, okay? Now, my presentation will follow the following structure. I want to give you an overview of our project, who is in the consortium, what are the phases we've been moving on throughout the project, some research that goes beyond the state of the art, what are we pursuing from an innovation point of view in the project, then what are the materials that we have analyzed as new solutions for these chassis components, and some results that we've obtained at different material scales, let's say. Okay, now regarding the Fatigue4Light project, this is a Horizon 2020 project. We've started to work in the consortium in February 2021, and we are close to finishing our project. We will end at the end of January 2024, so not much time left. The budget about 5.5 million. We've received funding for 4.9 from the European Commission. And our consortium is, I would say, a medium-sized consortium. We have 13 partners from 4 different European countries. Okay. The coordinator of the consortium of the Fatigue4Light project, as I said, is the International Center for Numerical Methods in Engineering, TIMNE, which is the institution that I'm representing today. Okay, so moving a little bit forward, our consortium is quite focused, I would say, on industrial partners. You see, because the main weight of the partners goes to industrial companies. We have 6 industrial companies in our consortium. For instance, Fiat, CRF, Magneto Wheels, which is a wheel manufacturer. We have Gestamp Hardtech, which brings their experience on heavy-duty electric vehicles. Then we have some material suppliers like ArcelorMittal. We have Profil Glass, who is our aluminium supplier. Composite Service Europe, a Swedish company who has helped us to develop the multi-material and also the composite solutions for our project. And I think that's all in terms of industrial companies. Then we have 3 research institutions like SIMNE, Eurecad also, and RISE from Sweden. 3 universities which have joined us during this interesting 3 years: Luleå University, Politecnico di Torino, and also the Polytechnic University of Catalonia, UPC, from here from Barcelona. And we also have one standardization body, which is UNE, who has been working with us to push forward the standardization for several experimental approaches targeting fatigue that we are proposing in the project. Okay, now just an overview of who the people behind these institutions are in our consortium. And these are some pictures from the consortium meetings that we've had throughout the project. Of course, we started as everybody during the post-COVID first years, let's say, with virtual meetings, but slowly we have migrated to seeing each other in person. And well, it has been a fulfilling experience. Maybe in the future, we will eventually start organizing also some webinars like this one in person. You never know, right? Okay, now regarding the project phases that we've passed through in the development of the Fatigue4Light work plan. You see, the first year was a very intense year, which was focused on assessing the behavior of the different materials we were studying, we were considering for lightweighting chassis components in our project. And during that first year, we've had an extensive experimental campaign where we studied the behavior at coupon scale of all of these different solutions. It was, as I said, a very intense year because we've had different experimental aspects that we wanted to consider, and I will share them with you later on. Second year, we wanted to move to a more complex scale, and this was the lab scale phase, let's say, where we had some laboratory demonstrator, and we focused on studying what were the effects of the manufacturing processes of typical chassis components on the behavior under fatigue or under loads that cause cyclic loads that cause fatigue behavior. Okay, also, and I would say during the same time, we've worked quite intensely on developing some new simulation methods to be able to reproduce numerically what was seen at experimental level, let's say. And this last year, this third year, has also been very intense, I would say, in terms of workload, but specifically devoted to analyzing the behavior at component level. Okay, so industrial demonstrator chassis component. And we've studied their behavior, of course, from the experimental point of view, but also from the numerical point of view. And this is what we want to share with you today, right? This comparison in between these two perspectives. Regarding the workflow, we've advanced, as I said, from material to component, focusing on some quite interesting and innovative experimental techniques, which I want to comment here because, fatigue experimental campaigns normally are quite lengthy and time-consuming, obviously cost-consuming also. So we've devoted an important part of the project to develop new testing methodologies which can help industry, can help research institutions to find in a more time-efficient and cost-efficient way what is the fatigue limit of a material, what is, let's say, the fatigue performance in terms of SN curve of a specific material. At the same time, new computer simulation methods, you will see more about this today, and taking all of these approaches until the most complex level, until this demonstrator, this component level. Okay, now, what is the research that we have pursued in the Fatigue4Light project beyond the state of the art, okay, beyond what is done normally or currently in fatigue analysis? Well, the main approach, or the main point I would say that's important to mention here is this comprehensive approach where we study the effect of the manufacturing processes on specific materials from this manufacturing, from the manufacturing of the component. Because as you know, everything that we do to a specific component will then affect its performance during its service life, right? And if you have different manufacturing processes, such as stamping, such as welding, trimming, cutting, punching, all of these different processes, which are normal, which are used on a day-by-day basis when you manufacture chassis components, they are definitely going to affect your fatigue performance. So from this point of view, we followed this approach in the project, where we took into account, well, the plastic deformations and all of the other effects from the manufacturing processes into the fatigue performance of the components later on. Okay, what are the materials that we've targeted in the project? Well, we have different groups. A very important work effort has been focused on the performance of advanced high-strength steel. Specifically for some applications, we've targeted complex phase 980, and for some other applications, CP800. Then we have some solutions that are considering hybrid materials, which is a metal composite sandwich material, okay? Also some new martensitic stainless steels, which were adapted for press hardening. And this is for solutions for chassis components for heavy-duty electrical vehicles. Then we considered press hardening steels, advanced boron steel, okay, also for heavy-duty electrical vehicle chassis, and also some aluminum alloys, which have improved fatigue resistance, and they have a high amount of scrap, okay, because we were interested in seeing the performance of materials that are very interesting from a recyclability point of view. So, okay. Now, regarding some results that we've obtained, as I said, at material level during the first year in our project, the experimental campaign was focused on 5 different points, and here I target the first 4. Obviously, we were interested in the performance of tensile behavior of each different type of material we've studied in the project. After that, we studied the local formability by means of a hole expansion test, the fracture toughness, and also some environmental effects by means of corrosion tests. And here you can see, I would say, different results for each type of test of how the different materials that we've studied ranked in terms of these 4 criteria. However, for us and for our consortium, the most important behavior, of course, was what we saw in terms of fatigue behavior. And we decided to approach the experimental campaigns on fatigue from several different points of view. For instance, we've definitely used the conventional staircase method, which is what everybody does in terms of testing nowadays, okay, in all the labs everywhere. But we were also interested, as I said, in proposing some new experimental techniques which helped reduce significantly the testing time for the different materials. And from this point of view, we've had the self-heating method, which was proposed by our partners at ArcelorMittal. We've had the stiffness method proposed by our colleagues at Eurecat. And we've also had an experimental campaign which was focused on very high cycle fatigue method, of course, with different failure mechanism, I would say, compared to the other behavior observed on high cycle fatigue specifically. And this campaign was done by our colleagues at Politecnico di Torino. And you can see here, for instance, an overview of how the different materials ranked in terms of specifically their fatigue limit normalized by the weight of the material. Okay, it was a way of objectifying, let's say, or having a more objective perspective on the performance in terms of fatigue limit, as I say, of the different materials. Okay, if you want to know more information about these experimental techniques that were developed during the Fatigue4Light project, I left here a link for a paper published on Science Direct. You can look at it there and find out more. I just want to say that an interesting information for you to take from this presentation is that, for instance, for if a typical fatigue experimental campaign performed with the staircase method would last, for instance, about 2 weeks. With these fast fatigue testing methodologies, you can reduce the testing time to about 4 hours, okay, and with only 3-hour glass specimens, and you will have the fatigue limit. So it's a very interesting approach. Okay. Now, second year of the project, we wanted to complicate the problem a little bit more, so go to higher scales. And we devoted some time for this lab scale demonstrator level. And we've chosen a demonstrator, which is this L-shaped profile, which has some holes, which are representative of, well, typical geometry that you would find, obviously including some holes on chassis components. We've dedicated some time to analyzing different behaviors in terms of polished component or unpolished component. Okay, so seeing a little bit what was the effect of these surface treating techniques. And the experimental campaign, which was done at lab scale demonstrator level, included several stress amplitudes with a reversion factor of -1, so fully reverse cyclic loading. And here you can see a comparison in between the life which was obtained through the simulation, the numerical analysis of this geometry, as compared to what was seen experimentally in the campaign done by our colleagues at Eurecat. You can also see the failure mode, which is observed below. And this is interesting because with the numerical approach that we've developed during the Fatigue4Light project, we've seen a really good agreement in between the life obtained at experimental level and in the numerical simulation. And here I have just a small sample of a video from a simulation. More details about the specific formulation which was used to perform this numerical analysis, you will see later on in the presentation given by my colleague Sergio Jimenez. Okay, let's move further. Okay, we go to demonstrator level, and here we have targeted several different types of demonstrators. I would say the one we studied most extensively was the lower control arm, and these are the presentations that you will see later on today, given by Michele Tedesco from Stellantis, and also by Matthias Merzik from RISE. So I won't be giving you a lot of detail here because they will explain better than what I can do how these different solutions for these demonstrators were developed. But I just want to show you a small video which was proposed by our colleagues at RISE, where you can see the manufacturing process of the hybrid version, okay, for this lower control arm. And this is very interesting because they've also had to manufacture the tool to build the demonstrator. And then, of course, construct this multi-material solution where you have the outer parts, let's say, of the geometry formulated in aluminium, an aluminium alloy, provided by Profil Glass, our partners in the consortium. And the core part is a glass fiber reinforced polymer. But as I said, Matthias will give you more information about this. Here's an overview of the demonstrator after the manufacturing. And this is, let's say, the final shape. Okay. Now, some other demonstrators that we pursued in the project. Let me see, like this. Okay. We've studied the performance of different materials for a wheel prototype, specifically the disc prototype for an SUV. Which was proposed to the consortium by our partner Magneto Wheels. And for this specific geometry proposed, a new stamping cycle was designed to be able to adopt new materials, specifically the CP800 steel, advanced high-strength steel. And it was very interesting because, for instance, for this specific demonstrator, current state of the art, it is manufactured in DP600, okay? And the innovation pursued in the consortium was to change and see how this geometry performed under CP800. But what was interesting was seeing that from the stamping process, let's say, the DP600 came out with improved fatigue properties, while the CP800 actually came out with diminished fatigue properties. And this is interesting. We believe it's because of the internal microstructure of each different material, of course. And after having built several demonstrators, several discs in CP800 with this specifically designed, specifically tailored stamping cycle, an extensive experimental campaign was done by our colleagues at Magneto Wheels, and you can see here a comparison between performance of different materials and also different thicknesses, because of course the idea is to adopt new materials so you can reduce the weight of the components, and you do this of course by also reducing the thickness. Obviously you want to keep the stiffness requirements and the strength requirements which are needed to pass all of the tests required. Here's an overview of a simulation that we've performed from Thimne, but I won't go into too much detail because, as I said, my colleague Sergio will give more detail on this. Here's an overview of where the cracks develop in the numerical simulation, and you will see how they compare with the experimental result. Okay, another demonstrator that was also pursued in the Fatigue4Light project, and you won't have a specific presentation about it today. This is why I'm mentioning it, is the cross-member beam, which is an element of a heavy-duty electric vehicle chassis. This was a demonstrator proposed by our colleagues at Gestamp Hardtech in Sweden. They chose a symmetrical design, so we manufactured only half of the part of the demonstrator. And here you can see a small video with the manufacturing. This is a demonstrator which was manufactured in 22 manganese boron 5 steel with a thickness of 6 millimeters. Okay. Okay. Now, this is the demonstrator which is screwed to the test benchmark, or to the test bench to be tested under fatigue and also under monotonic conditions. And this is the first approximation that we've done at Simne, studying the behavior in the elastic part for this demonstrator. And you will see the numerical behavior under fatigue in the presentation given by my colleague just in a bit. Okay. But as I said, the Fatigue4Light project has studied the behavior of all these different material solutions from the point of view, from the mechanical point of view, let's say, strictly fatigue mechanical behavior, but also it's very important for our project to have an eco-design perspective, okay? And we devoted, we had a specific team working on these eco-design aspects throughout the entire development of the project, and we've reached some very interesting conclusions because we are ranking at this point in the project each of the solutions developed for these demonstrators from recyclability perspective, obviously weight reduction perspective, energy consumption perspective, CO2 emission, a lot of different aspects which are quite interesting to consider, but we won't be devoting time to this today. So if you want to find out more about this part specifically, I want to invite you on the 15th of January to the third webinar that we will celebrate in the Fatigue4Light project, where we will speak exclusively about this part, okay, about eco-design assessment. Other than this, if you have more interest in our project, want to know more about our publications, please follow us in the social networks and LinkedIn and Twitter. We have a YouTube channel where we upload interesting videos, and also you can check our website. Okay, from my side, nothing more. Thank you for your attention. And this is a great moment for me to pass the word to Sergio, who will continue with the next presentation.
Okay. So thank you, Lucia, for your presentation, and thank you everybody for joining us on this webinar today. My name is Sergio, as Lucia mentioned previously, and I'm also a researcher in the Thymne Research Center, and I'm also coordinating this Fatigue4Light H 2020 project. My first presentation today will be dedicated, as Lucia mentioned previously, to introduce briefly some of the methodologies that we use in Thymne in order to characterize the monotonic and the high cycle fatigue response of the material from a numerical perspective. So in order to do that, I've structured my presentation into these three main blocks. First of all, I will really briefly present some of the constitutive laws that we use to characterize the monotonic response of some of the materials. Then I will move towards the characterization of the cyclic response, and specifically, I will be describing the high cycle fatigue constitutive model that we used in Thymne, and that we've been using in the Fatigue4Light project. And then finally, I will present some, let's say, minor case examples in order to see which is the application of these methodologies that I've introduced you. I really do not want to focus much in the formulation that support the methodologies, but on the main concepts and the ideas that control the workflow in each of the constitutive laws. But before going into this technical part of my presentation, let me first of all introduce the team in Thymne that has been working in this Fatigue4Light project, and in the sense that all the results that I will be showing today has been conducted by these researchers here. And in addition to this, I would like to tell you that constitutive laws that I will be presenting, they are all of them available in this open source Kratos Multiphysics code. So you can consult all of them. That all of these constitutive models are implemented in this finite element scheme, and that all the cases that I will be presenting are dedicated to study small strain and small displacement cases. So now let's start with the approach, the constitutive models that we use for the characterization of a monotonic response in materials. So basically, for characterizing the monotonic response of a material, we identify three different behaviors that govern the inelastic response of the material. So depending on this inelastic phase, we build different constitutive models. So in those cases where plastic strains are being accumulated along the inelastic phase of the material, we work with plasticity constitutive models. And in particular, what I'm describing here is this small strain isotropic hardening plasticity constitutive law, where the stress is being computed using this general expression which is related with the strain, the total strain, and the plastic strain appearing along the material life. And mainly the most important feature of this characteristic of this constitutive law is that it's it's completely described in energy dissipation terms, meaning that the inelastic response of the material is governed by the progressive accumulation of this fracture energy dissipation. And basically, this inelastic response is characterized by accumulation of plastic strains, changes in the strength of the material, and also this accumulation of the plastic energy dissipation. And then the yield criterion and the threshold functions are more or less common to other constitutive laws available for describing plasticity phenomena. Then when in those cases where plasticity is not accumulated along the inelastic response, but what we observe at the material level is the degradation of the stiffness of the material, then we should move towards damage constitutive loss. And in this case, I'm presenting here this basic isotropic damage constitutive model, where this stiffness degradation is controlled by this scalar parameter, this internal variable called damage internal variable, which ranges from 0 to 1, 0 corresponding to virgin material state and 1 to fully damaged state. This constitutive model is, again, energy dissipation based constitutive model. So the deterioration process, the degradation process is being described according to this dissipation process of the fracture energy. So along this inelastic process, what it's happening at the material level, it's the accumulation of damage parameter, the changes in the strength response of the material, and then, of course, the accumulation of this degradation process, right? Controlled by this damage dissipation term here. And again, the yield criteria and the threshold functions are more or less common to any other damage model. And then finally, for those scenarios where both plastic strains and stiffness degradation appears in the material, we should move towards a more sophisticated constitutive model to reproduce this behavior in the material. And this is what we call plastic damage models. So in this type of, well, from thinness point of view, we proposed, or from thinness side, we proposed two different methodologies. The first one is what we call the uncoupled plastic damage model. This model is based on the rule of mixtures, but we adopt here another point of view for this rule of mixtures law, where instead of mixing the response of two different materials, what we're mixing here is the constitutive behavior, different constitutive behaviors. In particular, we are mixing damage behavior and plasticity behavior. So by mixing them, we obtain finally the material response, this plastic damage material response. And the main particularity of this constitutive law is that it uses independent yield criteria for the plastic and the damage responses being controlled in the material. And then, of course, the degradation process in this case is being characterized by the accumulation of plastic strains combined now with the accumulation of damage and the evolution of the strength of the material. And but we also have this other plastic damage model, which is this coupled plastic damage model, where we only use a unique criteria to describe the yield criteria in the model. And again, here the inelastic process is again characterized by the accumulation of plastic strains. In this case, the changes in the compliance matrix and changes in the strength of the material. I will not go into details for any of these models, but in particular for this coupled plastic damage model, you can find more information and a complete review of the methodology in this publication here that we published last year. And then when moving towards the characterization of composite materials, and in particular towards FRP composites that are the ones being studied in the Fatigue4Light project, we use this serial parallel rule of mixtures approach. And this rule of this is indeed an evolution of the classical rule of mixtures, where for each of the layers of the FRP material, we distinguish two component materials, the fiber and the matrix. And for each of them, we can use any constitutive law. So at the end, what we are doing here is characterizing the component materials composing the composite, and then build up the composite response through this serial parallel rule of mixtures. And what is this mixture process? Well, this combination of the fiber and matrix response is based in this case on the orientation of the materials. So we define two characteristic directions that define the different behaviors for the composite. And the first one is this parallel direction, which coincides with the longitudinal axis of the fibers, where we impose this isostrain condition for the composite at the component level. And orthogonal to this direction, we define this series direction where we have isostress condition for the composite and the components. Of course, this formulation is not only applicable for FRP composites, but it can be used also for other long fiber composites like these cases here that I'm describing, where we use this methodology, this approach to characterize the behavior of pre-stressed concrete structures. Okay, you have more details for this methodology in these papers here. And now I will move to the core of this presentation, which is the cyclic response, the characterization from a numerical perspective of the cyclic response in a material, and particularly in the high cycle fatigue case. But let me first start by describing what's new with respect to the monotonic scenario. And the thing is that now in these cyclic cases, not only the stress is important, but the problem also depends on the amount of cycles being applied in the material. So depending on the amount of cycles, the response is one or another. At least this is what is observed experimentally. And this is this can be seen through this SN information or Buller curve information that relates the stress being applied on a sample and the amount of cycles that it takes to fail that sample. Of course, from this type of chart, we can retrieve monotonic and cycle properties for that specific material. So we can plot here also the yield strength of the material. We can also print here or point out which is the ultimate strength, and we can also compute in a certain manner which is the fatigue limit below which no fatigue degradation is expected. And also it is typical for this type of information to distinguish, as I was commenting previously, two regimes for the fatigue response in a material. What it's called low cycle fatigue and high cycle fatigue. And usually this is related with the amount of cycles necessary to fail that particular sample or that particular material. And meaning that if less amount of cycles are required, then these failures are related with what is called low cycle fatigue. And when more cycles are required, high cycle fatigue is then the phenomenon controlling the degradation process. But indeed, this is just the result. So this is when the failure takes place. But this is not really describing the phenomena taking and controlling the degradation process along the fatigue phenomena. What is interesting, it's checking that, realizing that these low cycle fatigue scenarios appear with presence or take place with presence of plastic strain accumulation, while in the high cycle fatigue cases, no plastic strains accumulation take place. So we can somehow relate this with what we've seen previously for the monotonic scenarios. And so instead of using and focusing on the result, so the amount of cycles, we can forget about the amount of cycles in the fatigue characterization and just focus on the stress being applied on our material. Because if we want to experience plastic strains, then we should go above the yield strength of the material. And the opposite can be also applied for the high cycle fatigue condition. So this means that from now on, while I will be describing the high cycle fatigue model, I will be just focusing on those scenarios where the stress state being applied on the material will be just below the yield strength of that material. And considering the fact that I will be presenting a constitutive law, I really want to point out the importance of describing the material behavior and not anything else. And I'm saying this because usually, well, not usually, this type of SN information, it's referred to mean stress, so engineering stress at the sample level, and failure of the sample and not initiation of the crack or maximum stress at the sample and so on. And this type of information is really important to be taken into account while describing the characterizing the constitutive model that I will be then be proposing. And I'm just exemplifying this through these standard geometries for fatigue analysis, where we can see which is the relation between the maximum stress in the sample and the mean stress that would be the one being reported at the SN as SN data. And you can see here that this relation, depending on the geometry, can go up to 10%. So this is something that should be taken into account along the analysis. Then now, in order to build or to describe the constitutive model that we've implemented in Kratos, I've just summarized some of the bullet points, some of the main characteristics that describe this high cycle fatigue phenomena. And then I will be connecting these main characteristics with some of the requirements that we need to fulfill in this constitutive law that we will be building now. So these are the requirements to be satisfied. Then let's work on the first one. So in order to achieve no plastic strain accumulation identified in this high cycle fatigue process, what we need to work with is a damage-based description for this high cycle fatigue constitutive law, which is the alternative to the plasticity constitutive model, right? As we've seen previously. This results in characterizing the stress in our high cycle fatigue model in this way, which is the same one that I present previously for the isotropic damage case. Then, as this high cycle fatigue process takes place, or the failure takes place in a brittle and sudden manner, and as I commented previously, the failure occurs for stresses below the yield strength, this needs to be reflected somehow in a different manner to the way that we used to do for the isotropic damage model. And the way that we achieve that is, first of all, by introducing, in addition to this, let's say, visible inelastic process that appear in the damage constitutive model, we need to introduce this hidden inelastic degradation process, or this fatigue response. It's exactly the same, where we somehow initiate the inelasticity process in a hidden, in a non-apparent way for stresses which are, for maximum stresses which are above the fatigue limit of the material, but we still satisfy the yield criteria described through this expression here. And basically what I'm doing, this is exactly the same yield criterion that I presented for the damage case, but now I'm introducing this term, which is the term that governs the fatigue response in our constitutive law. And I will describe it later. Just for you to know, this is a term, this fatigue reduction factor term ranges from 1 to 0, 1 for virgin conditions, and well, it's not necessary to be 0, but minimum level, I have some examples there where the minimum is set to 0.1. That progressively degrades or diminish the strength of the material, or here in this yield criteria, what I'm doing is amplifying the stress state of the material. Both are equivalent. And then in order to achieve failure below the yield strength, what we need to do is somehow reducing the strength of the material and the fracture energy along this fatigue response of the constitutive law. And we do that by diminishing, as I was previously commenting, the strength through this fatigue reduction factor, but also reducing the amount of fracture energy available in the material, and they result in this type of response. Okay, I have some examples afterwards, which may be more visible and evident of what I'm doing here. Then Another feature to be captured for this high cycle fatigue response in materials is this loading sequence effects, which is really related with the fact that the nonlinear process taking place along this fatigue response of the material, this fatigue phase of the material, should be nonlinear. And in order to achieve that, what we've done is describing this fatigue reduction factor as a function of the amount of the number of cycles being applied in the element, the reversion factor, which relates the minimum and maximum stresses applied in the appearing in the material, and the maximum stress level. And then finally, considering that usually this high cycle fatigue phenomena develops for, or the failure takes place for high, really high number of cycles, it is really advisable to have or to integrate an advancing time strategy together with the constitutive model. And we've also do that in the constitutive law that we're proposing. So this basically describes the main characteristics of our constitutive law. And now let's see how this constitutive model is being used and some of the main features coming from this constitutive model through some examples. So basically, in order to use this constitutive model, the first thing that we should do is characterizing the monotonic response of the material. So in this case, you can see the experimental results for a stainless steel metal and the corresponding calibration made from a numerical perspective. So from this type of analysis, basically what we are obtaining here is that we are calibrating our yield strength, the ultimate strength, but also the Young modulus, the Poisson, the fractal energy of the material. Then once we finish with this, we can move towards the calibration of the fatigue part of this high cycle fatigue constitutive law, which is based on characterizing the parameters that define this fatigue reduction factor function, which has this form here. This is the expression, the mathematical expression that governs this degradation in terms of strength and fracture energy. And in order to calibrate this function, it depends on 5 parameters, these 5 parameters here. And the good news is that this function can be connected somehow with the SN information, that it's the typical information that is reported experimentally for characterizing the high cycle fatigue response of a material. So based on this connection between these two, let's say, information in terms of fatigue, we also built an expression, a mathematical expression to capture this SN information through this Buller surface, which is based on exactly the same parameters that we used to define the fatigue reduction factor. Meaning that by calibrating this expression here, based on experimental data, we are automatically also characterizing the response of the constitutive law in terms of the fatigue reduction factor. And you can find more details about this, all these ideas in these two papers. And once we finish with this characterization process for both the monotonic and the fatigue response, we can start then with the simulations. So I've first of all present here a basic case in a one element finite element model, where I really want to emphasize which are the main features of this constitutive law. So basically what I'm doing here, first of all, is applying some amount of cycles in that element, and then apply a tensile test on that element and see what is the response of the material. So basically, we have here the monotonic response of the material as reference, and then what you can observe here is the response, this tensile response of the material. So we have here first the cycles, and then we have the monotonic response of the material in terms of stress strain curve after applying 71,000 cycles. And this amount of cycles results in moving from fatigue reduction factor equal to 1 to fatigue reduction factor equal to 0.8. And this is basically a representation of the SN curve the experimental data, and the fatigue reduction factor here in also plotted in this chart. And you can see here this big jump corresponds indeed to the advancing time strategy. So you can imagine that each of these cycles is being described through, in this case, each cycle it's 8 steps in the numerical simulation. So imagine trying to go through these nearly 100,000 cycles, well, these 71,000 cycles without no advancing time strategy. And the same with, I've done the same for other amount of cycles. So in this case, 77,000 cycles, and then the tensile test. And we can see how the strength and the fracture energy progressively decrease along the simulation. And then I also have these two other cases where, in addition to this strength and stiffness, strength and fracture energy degradation, we also accumulate stiffness degradation because we are already entering into this final inelastic response of the material where damage is also activated. So not only fatigue reduction factor, but also damage. And this really helps to understand which is the process, or which is the type of response predicted by this type of constitutive model. And now let me just move towards some application examples corresponding to the Fatigue4Light project. So first of all, as Lucia mentioned, we first dedicated the first year to study the material response of different materials that then are being used in the project to build the final Fatigue4Light solution for several demonstrators. So this first stage, in this first stage, we use the constitutive model to, well, we calibrate our constitutive model, and we were able to undergo some of these pure fatigue experiments. So reproducing some of the SN tests, and you have here some of the results obtained for high strength steel, and this one corresponding to a press hardened steel. But also we can also work in other more complex scenarios in which we work more or less in following a similar approach as the one that I was presenting previously. So I will not present anything about this, where we first of all apply several cycles, and then we move towards a pure tensile test, and we observe which was the strength degradation associated to that material as a function of the amount of cycles being applied. And I'm including this chart here corresponding to this stainless steel that I was previously characterizing, just because it's interesting to observe how this constitutive model is able to, or is interesting, one of the main features that it has is the ability of studying this crack propagation in the geometry being studied. In this case, this is just a coupon sample, but this applies to other cases. Then, using lab scale demonstrators like the L profile that Lucia showed, we also were interested in studying the effects over the fatigue response in materials that different manufacturing process introduce. So then, in addition to observing, to study this type of processes or this type of phenomena from an experimental point of view, we also try to reproduce this from a numerical point of view. In particular here, what you can see is a fatigue test performed in a trim sample. So basically what we are doing here is considering the same material properties that we obtain while characterizing the fatigue response for the virgin material. We introduce some roughness in the surface through changes in the geometry, and then we then run the simulation, the fatigue simulation, and we observe the changes in terms of the amount of number of cycles that it took to then fail this type of new sample. And we obtain here nearly 70 1,000 cycles to reach the failure, which compared with the experimental, it's more or less aligned. Then we also work in punching cases where we introduce residual stresses in this punch area. And again, using the virgin material properties and introducing these residual stresses, we run the simulation and we obtain this new failure path, which really matches the information reported experimentally. And finally, we also worked on some forming cases. In particular, what I'm presenting here is a case where we first introduce a tensile deformation in the sample, and the sample experiences some plastic strains. And once we have this initial deterioration level in terms of plastic strains, we then move towards a high cycle fatigue scenario. And then we were able again to reproduce, to capture the results obtained experimentally. The comparison is between the red points and the yellow points. And with this, I finish my presentation. I just include this final slide with some conclusions. And basically, this is just a summary of what I've been presenting to you. So basically, what you've seen is the application of these monotonic and high cycle fatigue constitutive laws that I've introduced previously. And then from the monotonic perspective, what I present you is several monotonic constitutive laws: plasticity, damage, and plastic damage, all of them energy dissipation based. And that allows us to capture this plasticity accumulation, the reduction in terms of stiffness, and there's cases where both plasticity and damage appear together in the material. And from the high cycle fatigue point of view, what I want you to transmit with respect to this constitutive law that I present you is that good news, it's easy to calibrate. The process is pretty much automatic, and it's based on SM data, which in most cases it's the basic data used to characterize the fatigue performance of a material. And then that this constitutive law allows a continuous description of the problem, not only because it allows to control the crack path, but also because we are characterizing not only one SM curve of the fatigue response in our model, but the entire space, including all the number of cycles, all the maximum stress levels, and all the reversion factor combination possible. And finally, I would like to mention that this is an optimized tool because it's been integrated in a open MP code, Kratos, and we are also using this advancing time strategy that allows us to perform the simulations that I've shown you previously in the order of minutes, hours. Okay. So thank you very much, and I think it's time to move to Mikel's presentation.
Thank you very much, Sergio. Let's put in presentation mode. So you should see in presentation mode, right?
Yeah, we've seen your screen.
All good, Michele, yes.
Okay, perfect. So briefly about me, as introduced by Lucia, I'm the global manager in Stellantis for metals and the anti-corrosion department, so inside the material engineering organization. And we are looking to the materials and coating applied on all our vehicle in terms of innovation and also development and utilization in the life. So today we will see together the application of advanced strength steel for a component that is in chassis, the lower control arm. So briefly, we will see what is the chassis perimeter. what we did for the lower control arms in terms of feasibilities of the stamping of the component, and after this assessment and the realization of the component, we performed physical test and virtual test, and we compare each other the results to see if we are able to predict in the proper manner the reality in virtually. And finally, the conclusion. So briefly, the chassis is an important area of the vehicle because is the area that permit to have the contact between the wheel and in general the vehicle to the road, and assure also the handling of the car. We can define this microsystem. So we have the steering wheel, pedal box, brakes, half shaft, wheels and tires, engine suspension, and vehicle suspension, in which the lower control arm is one of the key components. In terms of weight, if we are considering the light-duty vehicle full electric, you can see that in a pie chart, the chassis system cover roughly the 20% of the total weight of the car. The rest, the heavier component, heavier compound, let me say, is the body and the powertrain, in which the powertrain is also included the battery system. So about our low control arm, we start the activity to check the feasibility of the component, first of all, virtually. At the left of this slide, you can see the CP800 stamping simulation, which is the CP800, the current material that we are using or we have in mind to use for this project. In terms of stamping, you can see is a full green evaluation, so the component is feasible without any problem. At the right, you see the simulation that we carried out using the new material complex phase 980. In this case, the overall evaluation is yellow because you can see here. Okay, you can see here the FLD. Some points are near to the limit, while for the CP800 we are more safety margin. We took in consideration these aspects during the stamping of the component, and with the right adjusting of the tool setup, we were able to make the components. So this was the first achievement of the project. The second one was to stress the component as for the real life on the car, and here you can see the first characterization that we did on the component. The characterization is a fatigue characterization in which we fix we block in this area the component, and we apply the load in this direction. Making the simulation, we have seen that the first crack on the component appear in this area. Afterwards, the most critical area is this hole, in which from the edges of the hole start the cracking of the component, and after a second crack initiation in this area. Also at the bench test, we realized an equipment to block here the component, and we applied the stress plus minus 7.5 kilonewton. Here you can see the bench test characterization and the three samples that we characterize. From the real characterization, so the physical characterization, we have seen that at 13,000 cycles, the crack start were expected from the simulation. on the samples number 3, we push the characterization over than the 13,000 cycles in order to see how the cracks propagation works on the component. And you can see here some image that correlate the cracks that we had in the real component, and also this is the cracks that we have in simulation, in which we define a first primary crack location here and a secondary one here. This secondary one was recognized mainly in the third component, in which we went over the full test. So you can see here the crack that also in terms of length and the shape is completely similar to the one that we predict virtually, and the second one is in this zone like that. So for this simulation, the correlation between physical and virtually was very accurate. The second test was always about the fatigue, but in this case for the welding of the bush that we have in this component. So we did the test like that. So we block here the component, we block also here, and here with a displacement of 47 millimeter, we apply a load in order to stress the welded area. Here you can see the simulation results, and the crack is in this area. And here the real component in which the area is the same. So from the location of the cracking, we were able to predict properly the starting of the crack, while we noted a big difference in terms of crack starting. So in the simulation, we predict that the crack start at 84,000 cycles, while in the real life, the starting of the crack was over than 160,000 cycles. Justification of this difference is due to the welding process, because during the arc welding we are heating up the material, and so also the mechanical properties in the area near to the welding zone are different. And so it's very difficult to predict this on the FEM simulation. But on that, we are still continuing to work in order to be closer between the simulation and the real life. The last characterization is not a fatigue, but is a misuse. So a unique load applied in this direction with the component that is blocked here in the bush and also here. And in this image, you can see the simulation results in terms of deformation of the component. The target that we have to pass is for the elastic limit, we need to go over than 17 kilonewton. For the collapse, the minimum acceptance is 19.8 kilonewton, and for the shock limit is 21.4. Here you can see an image of the bench test. Here looking at the top is more clear. We block here the component, we apply the load in this direction, and we deform the component. Here, a comparison between the simulation and the real component. You can see that the shape of the deformation is similar, so the simulation work properly. And also in terms of curve, you can see in green there is the component tested at the bench, while in red and in blue the component test. So sorry, the contrary. The green is the simulation. The red and blue is the bench test that we did. So the results is not so far from the simulation. So Also, in this case, we found a good correlation between the physical and the virtual simulation. So we can conclude that the design, we were able during the Fatigue4Light project to stamp the lower control arm using the advanced high-strength steel, the CP980, instead of CP800, without changing the geometry, but just doing a properly set up of the die. The components were tested physically and virtually, and the correlation between real life and the simulation was very, very good. We were able to predict in most of the cases the correct starting of the crack, and also in some cases also the number of cycles. The material card they used were developed during the Fatigue4Light project and improved the simulation versus the commercial software. And last but not least, using the CP980, we were able to allow a wet saving of 12% without changing the shape and the geometry of a current component. If we have more freedom and we have the opportunity also to redesign the component, we could achieve the 20% of lightweight saving. And so these can support also the decarbonization of the vehicle. So that's it for my side. I leave now the speech to Matthias for the next presentation.
Thank you very much, Michele, and I hope for a smooth transition here. So everybody should hear me and see my slide.
Yes, Matthias, it's perfect. Go ahead.
Wonderful. Okay, so hello everybody. My name is Matthias Mertges, and I'm a senior researcher here at the Research Institute of Sweden, located here in Gothenburg. And I will talk a little bit today in the next 15 minutes about hybrid manufacturing and structural testing of a 3D shaped fiber metal laminate. At some point, you already saw the video that Lucia showed earlier, so the YouTube video, and which actually gives like an overview on how to build up such a fiber metal laminate. And these are also like the different steps that I'm going to present here. So to present the hybrid solution, so-called hybrid solution, meaning combining different worlds here. So the fiber composite world, then with metallic materials, and then to finally get this lower control arm. So basically it's like, create and break your own sandwich. And let's get started with understanding a little bit the deformation of composites here. Starting to understand, okay, in this case, the glass fiber that was used for this study, before then coming to a more complex geometry. We will just like start with the flat one. So a glass fiber layup, a so-called biaxial layup, plus minus 45 degrees. And in this case, we just consider like the dry weave. So here you actually see the orientation of the so-called reinforcing fibers. And at some point, which seems to be like whitish here, those are like stitch yarns with texturized polyester. And at some point to understand a little bit, okay, how should we do the layup? I'm not going too much into the design of this lower control arm, but it's more like to understand what kind of volume fractions can we achieve. There's a so-called compaction test. So we just like put up a certain layup. This is a biaxial layup, fibers pointing out in horizontal and certain thickness. We use 10 biaxial layers, so overall 20 single layers. And in that case, we just like compress them, pretty easy. And here we get, when you increase the pressure, you can very well imagine the thickness changes. So you get like from a compressive force towards a pressure and the change in thickness. How is that helpful? So at some point, it is to find the transition to the volume fraction. And the volume fraction is actually can be determined by knowledge of the amount of layers that you're using, well, you have to know something about your fibers, so the fiber density, the measured thickness, done, that's via the test, and then also the aerial weight, so the mass per area per ply. In that case, you can calculate a volume fraction out of this force displacement relationship here. And usually you can very well imagine if you don't put any pressure at all, well, then the fibers at that point are very loose. So we want to compress them, put them a little bit more together. If it's too much, well, they will just like break. And rough estimate for the process window is shown here. So at relatively low pressures. So what did we do here? Different layups were tested at some point or like manufactured. So here on the right side, you see the calculation. It's basically, well, the thinner the material, the higher the volume fraction, the calculation. And here are a bunch of measurements that have been determined via a burn off, so that only the fibers will remain. So that means like this calculation is based on the dry weave. Those are materials where we already have a composite, so we're adding some polymer resin to that. Porosity has been excluded, but you see overall as a rule of thumb that we are in the range of 45% volume fraction and a layer thickness of roughly 170 microns of a single layer in this case. Porosity has been included. Yeah. So, and then here is basically the two triangles of interest. So this is the material that we investigated later for hybrid material. Before we come to that, we know something about the volume fraction check, but now it's also, I mean, fiber orientation is very important. So coming to the complex shape here, the aim was using a very simple draping simulation just to make sure that the final 0-degree fiber direction is along the composite, the white leg of this lower control arm. Okay, so now what we're doing now is like, before we come to complex structures, understanding the coupon level. So specimens have been manufactured and some resin has been added to the fiber layup. Here you actually see a different layup. And what we see here on the specimen is that it has like a translucent character. Means you can place a camera in the back of this tensile specimen, and it's kind of like shining through that. So machine vision cameras have been used with like 8-bit cameras, so that we get like gray levels in the range of 0 to 255. And here actually see the extensometer while we're doing a tensile test. So in that case, we see here stress strain curve determined. And what we see through this 1.4 millimeter thick specimen, that it's getting darker. And this is an effect of the microcrack, especially in the 90 layers in between the fibers. And that's like one way of characterizing damage. So that means like here, the darker it gets, the more damaged it is. And what we see is that already at very low strain levels here, around 0.5%, we see that there's a drastic increase here. So why are we using that? So now comes like a rough estimation in order to determine the fatigue. I mean, Fatigue4Light project, fatigue results here. So we're using the stiffness or the slopes of those two separate areas. So that means like the first one, which is the Young's modulus, low strains determined. And here we also see this kind of kink, which is like correlated to this microcracking. And we have the second slope here. Here, just as a reference, like the RP02 value. And now the aim is to go to a strain-based SM curve as shown here. And how are those numbers determined? Well, we are using strain-related damage onset. Damage onset in the lower region, so at the knee, so where the specimen got darker, and of course full damage, which is the ultimate tensile strain here. So we use those two limits, and in between here, that's a model. So that's a rough estimate that from 100 cycles to 1,000,000 cycles that they're like this kind of behavior. If an airplane would be designed like that, I would not enter that. So in that case, we need a verification. Some tests have been done stress controlled here at fully tension loading. at 5 Hertz so that the specimen doesn't heat up too much. You see the results of the quasi-static testing and a proper SN curve where we defined the run out of the million cycles. So now how do we get to this strain-based? In that case, since the stress-related values were in the upper region, we used the second slope here, and here we go. It's actually good a coincidence, not a coincidence, but it's like very comparable results between the model and the experimental part. So now we're coming from the glass fiber reinforced composite and adding metallic layers. In this case, we are adding an hardenable aluminum alloy and aluminum magnesium silicon alloy in the heat treatment state T6. So this is what we call a hybrid or in a fiber metal laminate as shown here. So here we see the specimen and we're doing a tension test and we compare that to the T6 aluminum alloy and also the inlay to the glass fiber reinforced composite. So we have different types of failures here or deformation. First, we have pure elastic. The second part, so the second slope here, it's elastic plastic. Then we have the failure of the glass fiber inside the specimen. And then we have one layer aluminum layer that's failing and then the second one. So this is like elastic plastic deformation of the aluminum layer. And using the rule of mixture, again, the model in green, we can at least predict like the first two areas there. But of course, this has also been investigated in fatigue, but here the failure mechanisms are a little bit different. So here we actually see, which is not seen in the SN curve, but it's what I'm telling you is like at the beginning, the fatigue of the aluminum occurred. So also crack growth here, at some point also delamination in between the layers, and then the final failure of the glass fiber reinforced part. So this is what we are working on in order to also understand a little bit about the deformation and failure behavior here. Now getting a little bit more complicated because we want to actually form the material here in this complex shape. And now coming from the composite side, the fibrous composite side, we also have to understand a little bit about the aluminum. This is a video that you actually saw in the beginning. So at some point there was like a forming simulation done by Avan in order to understand, okay, what is actually happening? What is the shape of the material, the blank thickness of 0.8 millimeters. And what you see here is like, well, cracking occurs. How and why does that occur? In that case, a forming limit diagram was used. So in order to compare that also to the predictions, because as you might know, in order to get those numbers for forming limit diagram, you have to do a lot of testing, very complex testing, but based also of literature values and the similarity between the 6181 aluminum and the 6082 aluminum alloy. It is at some point also a little bit understandable how and why it broke. So we actually see here that we have like the highest strain in this region, well, in that case also predicted the cracking, and this could also be simulated. So these are the values here. If we have a closer look into this forming limit diagram in order to understand the actual forming behavior, we don't have to go actually in different areas because we have like a more or less concentration in this area here. Well, and if we compare that to uniaxial testing, of course, that cannot cover everything, but at least we can like play a little bit. What should we do in order to avoid this cracking? Although here we actually see it was already like reduced compared to the video shown. So how can we change that? And that was like done with the heat treatment state. So here you see a bunch of stress strain curves determined coming from the material delivered from profile glass in the heat treatment state T6. And what we did is was basically killing the heat treatment state T6. That means high and the temperature range of roughly 300 degrees C over a certain time, roughly 4 hours. And to what is the aim? Well, to increase ductility. And as you can see here, rough increase of the ductility of factor 3. Unfortunately, well, that was expected, and reduction in strength by 50%. But in that case, it was also possible to actually manufacture that and also to control the crack size and the cracking itself. So here, but besides that heat treatment state, it was also different shapes So how should this raw blank look like? Does it have a radius? What is the radius size? What is the overlap in the material, and so on? So many different procedures or different geometries have been tried out in order to find an appropriate one, and then also to do the manufacturing and to come to this three-dimensional fiber metal laminate. And now this is the outcome. So that's what you see in this YouTube video, which is coming out of the press, and some makeup here and there is needed, especially for testing, which means like removing also the resin and the fibers outside there, and adding the adapters for testing, because at some point we want to do some structural testing here. And for that, the aluminum adapters were used, and also to incorporate the bushings as needed. So it sounds like very comparable to what Michele showed earlier. And those joining, or that joining that has been done using adhesive, but not only to adapt or to incorporate those adapters, but also a plate underneath to also increase the stiffness. So we have like a 3D metal shape, three-dimensional shaped material, hybrid material, and a flat laminate glued on the bottom. And now it's like testing time. So what we did here is like doing a comparable test as Michele showed earlier. The load introduction was the same, just the orientation was a little bit different. So coming here from top, and it's quasi-static testing, and you see the structure here. And for that, digital image correlation has been used. In that case, we can actually get the absolute deformation of the whole structure itself. So what you actually saw here was that the lower control arm actually failed, and especially in this lower area here. If I let the video run again, hopefully that works. So if you focus in this area here, well, we kind of neglected the weakest link, and the weakest link here in this case is definitely the adhesive joint between the flat plate and the 3D laminate. So here you actually see like this kind of debonding that's happening, and then also leading to an instability of the structure. And with that, I thank you very much for your attention. And as you can imagine, it's not only the result of my personal work, but many other people have been involved regarding specimen manufacturing, preparation, as well as also testing of the specimen and also the structure. And with that, I hand over to you, Sergio.
Okay, thank you, Matthias. So I will share again my screen now and proceed with the last presentation for today's webinar. Let me just share my screen. Okay, so let's start with this final presentation, which is dedicated to see how we, from the numerical point of view, reproduce the experiments that the industrial partners have undergone on the demonstrators. And in order to do that, we will be using, or what we've done is just using the formulation that I've presented you previously. So here you have the 4 demonstrators that we've been studying experimentally. So the lower control arms, the steel, and the hybrid solution, a wheel, as Lucia mentioned at the very beginning of today's webinar, and this cross-beam member used in the heavy-duty electric vehicles. So the first step was converting these real demonstrators into the numerical models that you can see here. Of course, we take advantage of the symmetry conditions in the wheel and in the cross-beam member when possible, and then we start with the numerical simulations. I first of all will briefly introduce the results that we obtained for the lower control arm that Michele more or less presented, and also Matthias have give some overview of this work. But let me just give some more numerical point of view perspective for both cases. So starting with the lower control arm and focusing on the fatigue response, this was the first case study that Michele was mentioning. So you have here the boundary conditions and where we fix these supports here, and then we apply this cyclic force in this other end. This is the numerical model that we built using quadratic tetrahedron finite elements. And this is the type of result that we obtain in terms of crack propagation along the fatigue simulation. So these are the results that Michele more or less shown. I think that Michele, what was showing for this crack was not the damage itself, the damage variable, but the fatigue reduction factor variable. And what you can see here is indeed the progression of the crack in terms of damage. So as Michele mentioned, we can capture both the first crack and the second one for this case study here. And then going towards this second scenario, where we are then focusing on the weld area, this weld area here. These are the new boundary conditions that we applied in our model, fixing these two ends here and this in inner region, and we applied the force in this here. So we have the weld seam in this connection in this connection region here. So basically, this is the type of result that we obtain. Let me just zoom in to better see the progression in the crack path. So we have, first of all, this initial damage area, which matches with this region identified experimentally. And then at some point, it also starts to propagate the crack in this bottom region. It should, let me just look through the video, just to show you which is this progression. And of course, we are not matching, as Michele mentioned, this amount of cycles compared with the experimental result. But of course, this may be due to the huge uncertainties coming from the welding in this region here. But at least we can capture the failure mechanism and the crack taking place. And with this, I finish with the still solution for the lower control arm. And now we move towards the hybrid solution. As Matthias mentioned, we could not really go into fatigue experiments just because in the misuse scenario where we apply the monotonic load, we get this detachment between the aluminum layers in the demonstrator. But at least from the numerical perspective, we could be able to reproduce this monotonic response. And this is the comparison between the numerical and the experimental responses that we obtain for this demonstrator. And what we observe here is that the numerical model also captures this stress concentration in this edge region of the lower control arm here, meaning that we also can identify this potential problematic area in the connection between the two aluminum layers. But now let's move towards the two other demonstrators that have not been present previously. The first one is this wheel here, where we applied this conventional bending test. So this is the type of experiment that the experimental guys, in this case, Magneto Wheels partner, is performing for their wheels in order to check the fatigue response of the wheel itself. And we convert these boundary conditions applied experimentally into these ones here, which are equivalent. And basically what we are doing is we are restraining this region here, which is in contact with the surface. And we applied the bending through this torque force, through this bending force on this bottom layer of the wheel. And from that, then we perform the fatigue simulation. Here you have an overview of the finite element mesh that we use for conducting this simulation. And you can see here a comparison between the experimental result in terms of crack location and the one obtained numerically. So we can capture perfectly this type of crack pattern observed experimentally. And then we've performed this for several load levels, moment levels, and this is the type of result that we're obtaining. So we better capture this scenario with higher moment being applied in the wheel, but also in this lower case, experimentally, more dispersion is being reported, and we kind of our numerical result kind of fit within these results obtained experimentally. And this is the type of result that is obtained for the wheel demonstrator. And then finally, with regards to this cross-member beam demonstrator, which was manufactured by Gestam, we studied here indeed several types of loading scenarios. The first one, monotonic test, and then we move to the fatigue test. So basically, in this monotonic scenario and also in the fatigue scenario, what we're doing is fixing these inner surfaces of the cross member beam while applying a monotonic increasing displacement in this final end of the demonstrator. This is the numerical model, the finite element model that we use to run these simulations, again using quadratic tetrahedron finite element mesh. And this is the results obtained from the monotonic test and the comparison with respect to the experimental results, both in the positive Z direction and also when loading in the negative X direction. A better agreement is observed for the positive Z results, but you can notice here that there is some spurious initial degradation, reduction in the stiffness in the material that may be the explanation for some higher, let's say, higher differences in this monotonic response for the cross-member beam. And then finally, when moving towards the fatigue scenario, what we're doing here is just in this particular case, because we've done other, but I'm just presenting this scenario where we are applying this cyclic load in the Z direction for the cross member beam. Experimentally, they reported this type of fracture being detected in the demonstrator after 70,000 cycles, and we reproduce the same type of failure in terms of crack path in our numerical model, but we obtain this, or the crack initiates after 75,000 cycles, so really matching this, but then the final propagation, so this final crack path took place after 35,000 cycles more. And with this, I think that I've more or less present you, which are the results that we're obtaining by applying these constitutive models that I was presenting you previously at the demonstrator. So thank you very much, and I think that we can start now with the question and answer section of the webinar.
Thank you very much for this overview of the results from the numerical simulation, Sergio. And yes, we have quite some delay, but I see there are a lot of questions here in the chat that we can answer and address in this Q&A session. And if somebody else would like to make a comment, would like to, I don't know, speak and say something, please raise your hand and we will give you the option to comment whatever you need to comment. From my side, let me pass through the questions here and let's address each one of them one by one. Okay. So I have Paulo, who is asking us several questions directed for Michele, I see, right? Okay, in the welded component analysis, what is the methodology used to predict the fatigue life numerically? And specifically for the case where numerical life was 80,000 cycles and the test was in 160, and if those simulations were performed with Kratos software. Okay, Michele, do you want to say something? I think we can also answer from Siemens' side regarding Kratos, but if you want to comment something.
I think that Sergio, because that the simulation is the right person to address this. He already anticipated in the previous presentation some of these. I don't know if he has some other details about this point.
Yeah, indeed, Luis Antonio has been the one working on that, but I can answer the question. Basically, in this welded case, we use Kratos to run this simulation that Michele was showing with the crack propagation, and the one that I've been showing in my last presentation. And what we've done there is using the material properties for the base material, so the CP980, and for the weld area, we apply there other elastic material properties. So our guess for this variation in the amount of cycles being detected, difference between the experimental and the numerical, is basically due to the uncertainty on the changes that this weld introduces on the base material, but also on the characterization itself of the weld material. So basically, I think that this explains your question, right?
Okay, Paulo, if you have any other comments or you want to say something, as I said, raise your hand and ask and go ahead. Also, I see you have a follow-up question here regarding the geometries for the demonstrators, okay, and the load control arm, if they are available publicly. Okay, from my point of view, what I can say right now, they are not available publicly. This is internal know-how of our consortium. We are working on publishing the results that we have obtained during the project. So for sure, in the future, some information will be available publicly. To what degree of precision, let's say, or of specific information, it remains to be determined. Okay, here we have to discuss with Michele, because this is CRF property, specifically the geometry of the load control arm. And of course, we need to adhere to their confidentiality policy, let's say. So whatever Michele wants to disclose will be disclosed. From Siemens side, everything is.
Yeah, probably we can discuss in a specific meeting with Paulo this kind of activity to understand what is his goal and so on. And for sure, when the vehicle is in the road, there is no problem to disclose the information before is not possible.
Okay, thank you so much, Michele. Okay, let's see. I'm going to move to Christian Stewart's question. Here we have a comment stating the fatigue test methods, okay, that were mentioned to find the fatigue limit in a reduced time, okay, have been used and validated for metals. You are totally right. There isn't much evidence of these methods working for FFP composite. True. Did you apply them? Yes. Okay. Let me comment on this. Regarding the self-heating method, the team at ArcelorMittal tried to apply it on composites. They didn't manage to find any conclusive results, okay, because their method is based on detecting a change on the stiffness of the material when you increase on the temperature that is recorded in the material, not the stiffness, when you increase different amplitudes, for the thermal part. But they couldn't reach a conclusive effect, as you say, on the FRP. However, when the team at Eurecat, who proposed the stiffness method, tried to apply this methodology, the stiffness methodology, to the composites being studied in the Fatigue4Light project, they did manage to detect quite well the fatigue limit for the FRP specific composite. Okay, So I would say there are different methods being proposed, and definitely some kind of analysis needs to be done previously to detect in a specific case that you are interested in applying, which is the best method for that specific material. Because as you see, for the composite case, one method works, one method doesn't work. So on a case by case basis, I would say you would have to well, dedicate some time and make some important decisions before analyzing which is the method for you. If you have any other comment, follow up, right here, Christian, and we can discuss further. Okay. Okay. Can you share some insights on the computational time? Okay, from Paolo Refatin. Okay. Required for the fatigue analysis using the proposed methodology. Great question. Well, everybody working in the simulation field, right, is super interested and super worried about the computational time, because definitely for fatigue computation, where you have specifically such long lives, computational time is super important, right? So Sergio, do you want to comment on the different computational time for different simulations that we've performed in the project?
Sure. It really depends on the size of the model for sure, and really depends on the initiation and the propagation of the crack. So basically, referring to this part here of my presentation, when describing the inelastic process of the high cycle fatigue constitutive model, distinguishing between these three inelastic responses, depending on when we move from this pure elastic to fatigue response, and then to also accumulate damage, and how the propagation of damage takes place, the model will stay long or less. In the simulations that I present here, so all these type of simulations, as I was commenting in the conclusion sections, that the order, the time is between minutes and hours, depending on the case study. In these ones, it took only minutes to be run. But in this case here, considering also this residual stress case information, it took hours because we identified non-linearities since the very beginning. So from that point on towards this final propagation, although we could apply also some advance in time strategy, we need to move little by little. This means time. And then when moving towards these big demonstrators, where now you can see the amount of finite elements used to build the finite element mesh in each of the demonstrators. Of course, the simulation takes longer. But for example, in the wheel, that case, it takes hours to be run. I think that I spoke yesterday with Alejandro, and I think that he told me that the last simulation he ran, well, it took like 5 hours, if I'm not wrong. In this case, it also took hours, not the monotonic one, but the fatigue one, which is the one that you were asking for. And case of the lower control arm, it took 2 days, right, Lucia, for this?
Yes.
In the weld, if I'm not wrong. And
for the
no.
For the weld, it took 1 day and 1 hour, I think. Okay. So it's like 25 hours. And for the fatigue case, purely fatigue case, it took longer. We spent like, I think 2 days, nearly 2 days.
I mean, just initiating. So up to this point, it's really fast because you jump from the second phase in the material towards the propagation of damage. This is really, really fast. The problem here is that you need to propagate the crack and then initiate the propagation and propagate the second crack. So that's why this type of simulation really took a long time. Because from that point on, you are already in the inelastic domain always. And that's the point. But compared with commercial techniques, what they usually do is just running up to this point, because the usual commercial approach is just based on stress distribution. So basically what they are doing there is guessing which is the amount of cycles that takes for each of the region, each of the points in the model to then degrade. But if you want to really then experience which is the degradation process in the demonstrator, it takes time.
Also, I would like to add here that a very important influence on the computational time is, of course, the cycle jump that you set up your simulation to run with, right? So you can do this cycle jump in the elastic regime, and you go directly to when damage begins, super fast, as Sergio says. You get there in, I don't know, maybe 1 minute, something like that. But after that, you're in the nonlinear regime, and you still have to do some cycle jumps, right? So depending if the size of your cycle jump is 1,000 cycles or if it's 100 cycles, wow, the computational time varies a lot. Okay, so you can go from 1 day to 7 days if you put the cycle jump at a very small level. I don't know if this answers your question, Paolo, and if you have any follow-up comment. I see there is a follow-up from Christian. Okay, any data published for the stiffness method when applied on FRP? No, this is not published. This is work done in the project that our colleagues at EURECAT have, let's say, the intellectual property on, and I believe they are working on publishing this. They've already published stuff for, I mean, the basis of the method and how it works for steels, okay, for different types of steels. That you can definitely find information. FRP is to be continued in the near future, I hope. Okay. Okay. Thank you, Paula, for your comment. Okay, we've gone quite a bit over the estimated time, but I don't want to close without giving the opportunity to our attendees, sorry, to our public, to have any comment, any issue that they want to put on the table. Okay. So okay. Thank you, everybody. If you have any other doubts, comments you want to pursue, and more information that you need from us, write to us by email, and we'll be very happy to answer all your questions. Thank you, and let's meet again in the next webinar if you have time. Okay? Bye-bye. Thank you all for attending.
Goodbye.
Thank you all. Bye-bye.